Welcome to the lesson on the parallelism tolerance. The goal of this lesson is to interpret the parallelism tolerance. When you're finished with this lesson, you should be able to describe what controls the parallelism deviation between two parallel surfaces where no parallelism tolerance is specified. Describe the terms parallelism and parallelism tolerance. Describe two common tolerance zone shapes for a parallelism tolerance. Recognize when a parallelism tolerance is applied to a planar surface or to a feature of size. List two indirect parallelism tolerances. Describe the modifiers that may be used in a parallelism tolerance. Describe real-world applications for a parallelism tolerance. Interpret a parallelism tolerance applied to a planar surface. Interpret a parallelism application that uses the tangent plane modifier. Interpret a parallelism tolerance at RFS applied to a diameter. Interpret a parallelism tolerance at MMC applied to a diameter. Understand parallelism verification principles. Describe how a parallelism tolerance applied to a surface is verified. Describe how to verify a parallelism tolerance at RFS applied to a feature of size. Describe how to verify a parallelism tolerance at MMC applied to a feature of size. It will take approximately 30 minutes to complete this lesson. These are the new terms introduced in this lesson. It's important for you to know these terms in order to understand the parallelism tolerance. Wherever a planar width or regular feature of size is shown on a drawing, rule number 1 applies, and the parallelism of both surfaces is controlled by the limits of the size dimension. Although this may be satisfactory in many cases, there are two shortcomings. The first is that the parallelism deviation is limited to the same tolerance as the size dimension. The second is the lack of a datum reference. As you can see in this figure, the part could be inspected using either side as the implied datum, which could result in different measurements by each inspector. Parallelism is the condition where a surface, axis, or center plane is equidistant at all points from a datum plane or axis. Since parallelism, the perfect condition, cannot be produced, you must specify some allowance for parallelism deviation. A parallelism tolerance is a geometric tolerance that limits the amount a surface, axis, or center plane is permitted to deviate from parallelism relative to a datum reference frame. Since parallelism is an orientation tolerance, it does not control the location of the toleranced feature. Even if the datum reference frame is established from three planar datum features, only the rotational degrees of freedom are constrained. The translational degrees are not. In other words, a parallelism tolerance zone can translate but not rotate relative to the datums.
What limits the deviation in parallelism between surfaces A and B? You're correct. The parallelism deviation is limited to the same tolerance as the size dimension. Click the right arrow to continue. One problem with using a size dimension to control parallelism is that it is not clear which surface should be used as the implied datum. You're correct. Click the right arrow to continue.
The two common tolerance zones for a parallelism tolerance are two parallel planes and a cylinder. The default shape of the tolerance zone is two parallel planes, parallel to the datum reference and separated by the tolerance value. This figure shows you an example of the second common tolerance zone for a parallelism tolerance, a single cylinder. Where the diameter modifier is placed with the tolerance value in the feature control frame, the tolerance zone is modified to a single cylinder, parallel to the datum reference and the diameter of the tolerance value.
What is the shape of the tolerance zone for the parallelism tolerance? You're correct. The default tolerance zone shape of two parallel planes for the parallelism tolerance applies. Click the right arrow to continue.
Two ways to specify that a parallelism tolerance is to apply to a surface are shown in the left panel. You may apply a parallelism tolerance to a planar surface or to a feature of size. If you apply it to a surface, the tolerance zone is located by the surface. The tolerance zone is shown on the right. When a parallelism tolerance is applied to a surface, the tolerance zone limits the deviation of the surface. The left panel shows how to specify that a parallelism tolerance is to apply to a feature of size. When you apply a parallelism tolerance to a feature of size, place the feature control frame below or beside the size dimension. The tolerance zone is shown on the right. When you apply a parallelism tolerance to a feature of size, the tolerance zone limits the deviation of the center plane. There are several geometric tolerances that indirectly affect the parallelism deviation of a planar surface or feature of size. Location tolerances such as position and profile of a surface can indirectly limit parallelism deviation. A size dimension or a dim origin dimension can also limit parallelism deviation. In these applications, the parallelism of the toleranced surface or feature of size is not directly inspected. The effect on parallelism deviation is a result of the toleranced feature being within the location tolerance zone. If you specify a parallelism tolerance and a location tolerance with the same primary datum reference frame on a feature or feature of size, the parallelism tolerance must be a refinement of the location tolerance.
On this drawing, what does the parallelism tolerance apply to? You're correct. The parallelism tolerance is attached to an extension line of the surface, indicating that the tolerance applies to the surface. Click the right arrow to continue.
There are several modifiers that may be used with the parallelism tolerance. This chart shows you these modifiers, their effects, and examples of functional applications.
What modifier could be specified in the tolerance portion of the parallelism tolerance shown on the drawing? You're correct. The tangent plane modifier is a valid modifier for this application. Click the right arrow to continue.
There are many real-world applications for a parallelism tolerance. Three typical applications are shown here. On the left is an application where a parallelism tolerance could be used to control orientation, to ensure a distributed load, and to reduce wear. In the center is an application where a parallelism tolerance could be used to control orientation to maintain a minimum gap between components of an assembly. On the right is an application where a parallelism tolerance could be used to control orientation to ensure linear motion with binding.
Which application is a real-world application for a parallelism tolerance? You're correct. Maintaining a uniform gap is a real-world application for a parallelism tolerance. Click the right arrow to continue.
On the left is a drawing that shows a parallelism tolerance applied to a planar surface. This is the most common application of a parallelism tolerance. The interpretation of the parallelism tolerance is shown on the right. Note that the part is oriented on datum plane A. In this example, the following conditions apply. The tolerance zone is the space between two parallel planes. The tolerance zone is parallel to the primary datum plane. The parallelism tolerance defines the distance between the two planes. Since all points of the toleranced surface must be within the tolerance zone, the parallelism tolerance also limits the flatness of the surface. The drawing on the left shows a parallelism tolerance with a tangent plane modifier applied to a planar surface. The use of the tangent plane modifier indicates that the tolerance zone applies to a plane that is tangent to the high points of the surface. Since the parallelism tolerance only applies to the high points of the surface, the flatness of the surface is not controlled. The interpretation of the parallelism tolerance is shown on the right. Note that the part is oriented on datum plane A. In this example, the following conditions apply. The tolerance zone is the space between two parallel planes. The tolerance zone is parallel to the primary datum plane. The parallelism tolerance defines the distance between the two planes. The tangent plane of the surface must be within the tolerance zone. The tolerance zone does not limit the form of the surface.
A parallelism tolerance applied to a surface limits orientation and location deviations. You're correct. A parallelism tolerance applied to a surface limits orientation and flatness deviations. You're correct. When the tangent plane modifier is specified in a parallelism tolerance, it does not limit the flatness deviations of the surface. You're correct. Click the right arrow to continue.
On the left is a parallelism tolerance at RFS applied to a hole. Where a parallelism tolerance is applied to a feature of size dimension, the tolerance zone applies to the axis or center plane of the unrelated actual mating envelope of the feature of size. The interpretation of the parallelism tolerance is on the right. In this example, the following conditions apply. The tolerance zone is within a cylinder. The tolerance zone is parallel to the datum plane. The parallelism tolerance defines the size of the tolerance zone cylinder. The axis of the unrelated actual mating envelope must be within the tolerance zone. The drawing on the left shows a parallelism tolerance at MMC applied to the hole. Where a geometric tolerance is applied at MMC, the function is often assembly and the surface interpretation is often used. Where parallelism tolerance at MMC is applied to a feature of size dimension, the tolerance zone applies to surfaces of the feature of size. Simply put, the surfaces of the feature of size may not violate the virtual condition, acceptance boundary. The interpretation of the parallelism tolerance is on the right. In this example, the following conditions apply. The orientation of the surface of the hole is related to the function of the hole. The surface interpretation is used. The tolerance zone is a virtual condition, acceptance boundary. The virtual condition acceptance boundary is parallel to the datum plane. Note that the total parallelism tolerance allowed increases as the hole departs from MMC towards LMC. This increase is the bonus tolerance. If you'd like to learn about why the surface interpretation is preferred over the axis interpretation, click on the button labeled Explanation.
What does a parallelism tolerance, RFS, applied to a cylindrical feature of size affect? You're correct. A parallelism tolerance, RFS, applied to a feature of size dimension, affects the axis or center plane of the unrelated actual mating envelope of the feature of size. Click the right arrow to continue.
This part of the course contains a simplified explanation of verification principles and methods that can be used to inspect a parallelism tolerance applied to a planar surface, a cylindrical feature of size RFS, and a cylindrical feature of size MMC. When parallelism is applied to a planar surface, the deviation is measured by finding the distance between two planes that are parallel to the datum and within which all points of the surface are located. When parallelism RFS is applied to a cylindrical feature of size, like a hole, the deviation is measured by finding the cylinder size that simulates the unrelated actual mating envelope. Then the axis of the actual mating envelope can be verified. When parallelism MMC is applied to a cylindrical feature of size, like a hole, the deviation is verified by passing the virtual condition cylinder, which is parallel to the primary datum, through the feature of size. Since parallelism does not control location, the inspection method should not be influenced by the location of the toleranced feature. There are many methods used to verify a parallelism tolerance. Here's an example of one common method using a surface plate and a height gauge. The drawing on the left shows a parallelism tolerance at RFS applied to a planar surface. The diagram on the right shows how to verify the parallelism tolerance. The part is mounted with datum feature A on the surface plate. The height gauge is moved across the surface plate, which moves the dial indicator across the part surface. The dial indicator reading must be equal to or less than the parallelism tolerance value.
One verification principle for parallelism tolerances is that the inspection method should include the effects of the location of the toleranced feature. One verification principle for a parallelism tolerance RFS applied to a hole is that the inspection method should determine the cylinder size that simulates the unrelated actual mating envelope, has an axis parallel to the primary datum. You're correct. Click the right arrow to continue. When verifying the parallelism tolerance shown here, what does the tolerance zone apply to? You're correct. The tolerance zone applies to all points of the surface. Click the right arrow to continue.
Take a look at this example showing how to verify a parallelism tolerance at RFS applied to a feature of size using a surface plate, a gauge pin, and a height gauge. The surface plate simulates the primary datum. The part is rested on the surface plate. A best fit gauge pin is placed into the hole to establish the unrelated actual mating envelope of the hole. The height gauge is used to measure a point on each end of the pin to establish the parallelism deviation of the hole relative to the datum. When a parallelism tolerance is specified at MMC, the surface interpretation is often used. There are many methods used to verify a parallelism tolerance using the surface interpretation. This example shows how to verify a parallelism tolerance using a functional gauge. The drawing on the left shows a parallelism tolerance at MMC applied to a cylindrical feature of size. A diagram showing how to verify the parallelism tolerance is on the right. Because the parallelism tolerance does not control the location of the hole, the pin must be able to move up and down to allow for the hole location deviation. The size of the gauge pin is equal to the virtual condition size of the hole, a 10.1 millimeter diameter.
Which inspection tool is often used to verify a parallelism tolerance applied at MMC? You're correct. A functional gauge is used to verify a parallelism tolerance applied at MMC. Click the right arrow to continue.
These topics are recommended for further study to improve your understanding of the parallelism tolerance. You've just completed the lesson on the parallelism tolerance. If you're not confident in your understanding of these topics, review the information before proceeding. Close this window to exit the lesson.